Hi, welcome to this session. Today I'm going to present a service model that complements the lack of end-to-end service guarantees in the modern day internet. Let's begin by looking over how the internet works today. The internet can be broadly defined as a network of autonomous systems, which represents a collection of routers and networks under a single domain. These autonomous systems are spread across the world and they peer with each other bilaterally using Border Gateway Protocol or BGP. The protocol dictates a set of relationships that helps the autonomous systems establish trust and paths across themselves globally. Traffic in the internet originates as well as terminates at endpoints that are part of periphery autonomous systems called access networks. When an access network receives traffic destined for a remote endpoint, one that is not part of it, the traffic gets routed across a series of autonomous systems. We call this as inter-domain routing. Whereas when it receives traffic destined for a local endpoint, one that is a part of it, the traffic gets routed across nodes within the same access network. We call this as intra-domain routing. End-to-end reachability in the internet requires routing operation across both inter-domain and intra-domain network elements. However, they operate independent of each other. That is, one cannot influence the other. Just as how an autonomous system or its endpoints cannot control the intra-domain routing elements of another autonomous system, end-to-end paths at inter-domain level also cannot be governed by any single operator or its endpoints. Rather, they are based on local decisions that are made at the individual autonomous systems. Moreover, due to the large number of operators and their autonomous nature, it has become difficult to overcome this limitation, making it even more difficult to enable endpoints to gain control of end-to-end paths in the internet today. Also, the internet today is mainly used for high-value content delivery. As much as the content generates financial benefits for the providers, the current paying policies in the internet define a financial model for the ISPs en route that does not provide a mechanism to share revenue generated by the delivery of content. Major players of large private clouds such as Google, Amazon, and Facebook have sought to build their own global infrastructures in response to these inadequacies of the internet. These global private network backbones not only interconnect the data centers of their operators globally, but also reach out to the various peering facilities at the edges of the internet and distribute content across them. Today, they have established direct peerings with a large number of access networks across the world, enabling content consumers to access content with just one autonomous system hop away from their access networks. In a related work, Zero-hop networking, it was proposed to bring content provider control directly into the access networks by virtually merging the two networks into a single domain. The idea is not only to enable consumers to access content as if it is part of their own network, hence the concept of zero-hop, but also to introduce a platform for end-to-end path control. However, as much as this would help the operators improve quality of content hosted across their own networks, content hosted elsewhere would still continue to use public transit. We are working on a service model that can utilize these global private infrastructures to offer end-to-end service guarantees for all such content. We call this model as private internet. In our model, these private network backbones act as transit providers, and we call their operators as private internet operators. They provide transit for content hosted by content providers without global infrastructure in the access networks. They not only enable communication between content providers and content consumers in the access networks, but also control and optimize the end-to-end service path across them and the backbone. Our model not only promotes a new business domain for the participating private internet operators, but also supports emerging content providers by guaranteeing better end-to-end traffic performance and provides more options to the content consumers to initiate end-to-end communication with the content providers across multiple private internet operators. To give a better idea of what we are trying to achieve, we have prepared a sample architecture based on our vision of the proposed model. This architecture essentially uses software-defined networking concepts to establish control across elements in the model. As you can see, both AN1 and AN2 are access networks that operate their networks using SDN. They're part of the same private internet PI1. The PI1 backbone here is a part of a global private network operated by the operator of PI1, which is PIO1 or Private Internet Operator 1. This architecture assumes that PIO1 also uses an SDN-like deployment in its backbone. It hosts an SDN application that acts as a client for the controllers in the ANs. In this sample architecture, control and data messages are communicated across separate network interfaces. The main purpose of control messages here is to help establish the path for the data messages. This architecture hence uses the private internet only for communication of data, whereas control messages are separately communicated across the controllers and the SDN application over the public internet. This is a sample workflow following the architecture that I just showed you. Here, server 1 in AN1 wants to send data to client 1 in AN2 across the private internet. When it sends its first packet, the switch that is adjacent to it in AN1 buffers the packet and sends it to AN1 controller. The controller then sends a network configuration request piggybacked with the current network state of AN1 to the SDN application running in PI1 via public internet. The app, upon receiving the request, tries to find the location of client 1, which is AN2. The app then requests AN2 controller to provide reachability information for client 1 in its network. Once the app has the necessary information of network from both the access networks, it sends this information along with that of PI1 backbone to the optimizer module. The optimizer evaluates the information against already provided service level agreements or SLAs to produce the optimal end-to-end path between server 1 and client 1 in PI1. The app then deploys the backbone part of the end-to-end path in its operator network and instructs AN1 and AN2 controllers to deploy the remaining part of the end-to-end path in their networks. Once the path is set up, the controller at AN1 instructs the switch to forward the buffered packet. All future packets that have the similar footprint or traffic class are forwarded along the same path. Currently, we are working on several components of this model, an architecture to find answers to the following questions. How can an access network ensure that traffic from multiple private internet operators are isolated from each other? How can the backbone part of the end-to-end path be deployed to handle inter-access network traffic and control? How can the endpoints determine which private internet to utilize from among multiple private internets available at the access networks? How can we implement routing and control in such a multi-network environment in a scalable way? I hope you enjoyed this presentation, and now I'd like to hear your thoughts and opinions about it. Thank you.